The star itself was about 200,000 or 300,000 solar luminosities. Okay, so we can measure changes in the brightness of the star at the level of a few percent. Okay? This star did not do anything in its last decade, which is interesting because there are a number of papers out there saying that it did do something. But basically what we'd say is that dead flatness means it didn't. That basically anything you would do to adjust the photosphere or drive a strong wind, and any of these strong winds people are talking about would almost immediately form dust. And all of that would be sort of trivially variable, trivially visible in this sort of data. And so we now have sort of 4 type 2Ps where we can sort of set these sorts of limits, and none of them are doing anything before they explode, which is sad. I mean, it would have been so much more fun if they did do something. Because we sort of joke about it as, if they did do something, you could draw circles of death. You say, that guy got a circle of death, now we just have to wait for it to explode. But no luck so far. And so in fact, our limits is basically, we're getting down to limits of the very typical variability of red supergiants. Is we're not quite sensitive to Betelgeuse-like variability, but we're not that far off from just being able to detect variability like you would see in Betelgeuse. So, what does that say is, well, so clearly some supernovae do something before they explode, okay? And clearly it's not typical, okay, because these are the most common supernova, and as far as we know, they're pretty much garden variety supernova. And so this comes to the question only some stars do this. And so then the question is, what is the physical variable that controls it? So, in general, these things are going to be the things which are, they're going to be the same as SMART's red supergiants. So these are things which are 8, 9, 10, 11, 12, 13, 14, 15 solar masses. And so the evidence is they don't do anything. And so there's some other, there's some mass range which does this. Maybe it's not mass. Maybe it's, you have to have the right metallicity. You have to have the right rotation rate. You have to have undergone some binary interaction. It's just not clear, but at least we now know that these stars don't do that.
Could it be binary companion? The lack of,
could be, because for example, is if you're a close binary, right? You would end your life with a very different rotation rate, as an example, as compared to spinning down, and the whole question of binarity of supernova, the whole binary, that's actually I'll talk about in whatever the short talk is actually worried about finding binaries, is very interesting. For these extragalactic ones, it's very hard to study binarity. Is you can only see, right, because the problem is just because of stellar ages, right, if your binary companion is even a little less massive, right, then it hasn't evolved, and so it's a main sequence star. And so blue main sequence stars actually turn out to be quite difficult to observe at distances of 10 megaparsecs given the available data. And so if you try to use the HST data to ask about binarity, you can really only detect the very brightest binary companions. The other problem is an interesting conflict between, there's 2 communities which don't talk. So the people who go looking for binaries, companions to the supernova in these HST data, and sometimes they claim to find them. And then there's another big community which is worried about dust formation in the early universe and dust formation in general, and want to make supernova a major source of dust. And so, for example, 87A, in modern ALMA observations in Herschel, it looks like it formed, something like a solar mass of dust, right? So, but if supernova form dust, then you cannot find their binary companions, right? Because the binary companion for a century, because the binary companion is behind a solar mass of dust, and it would just be completely blacked out. And so those 2 communities, as far as I can tell, never talk to one another. And so, but there's an inherent contradiction. Is if anyone has found a binary companion to a young supernova, then supernova don't make dust. If supernova make dust, then no one is ever going to find a binary companion to a young supernova. So one or the other of these camps is wrong. Okay. So as I said, this begins to say is you can begin to map out who doesn't so far. As I said, I would be much more excited if I found one who did vary. So I think what really is interesting is to see when we first get a type 2n, which we should get eventually, is to see what a type 2n does before it explodes. But that is what exactly allows things to know that they're about to explode. Because you can do a little bit of statistics. Is that if you have a supernova with this sort of dense material, it has to be associated with carbon burning or later. To see any of these events at all, it can't be a random occurrence in, say, the post-main sequence lifetime. It really has to be an occurrence associated with the end of life in order for the statistics to make any sense. And so somehow some of these stars do, in fact, know they're about to explode. And the question is which ones and why. OK, so summary is, well, we have a candidate for a failed supernova. We found one. OK, it's better than 0. It would be nice to have 2. It would be bad to have 10. Right? If we had found 10, then we would know we were screwing up. Right? Because that would be impossible. Right? So, 1 good, 2 better, 10 bad. Right? There has all the right properties to explain this story. The main proof is, well, for the moment, the main proof is we just sit there and make sure it doesn't come back. It hasn't come back. The one way you can try to hide it that you can plausibly say is this question of dust, is that if you put it behind enough dust, then you could obscure it in the optical and even the near infrared. That can be hopefully trivially solved by there's this thing I'm told we're going to launch any day now, that you can't hide it from JWST at like 20 microns. So if you were obscuring it by dust, you would just see it as a bright 20 micron source. Otherwise, you just keep watching, because the property of any dust formed in a transient is it keeps expanding. And so the optical depth drops as 1 over t squared. And if you just wait long enough, you have to be able to see through it. And so if JWST does not go up, then patience will still work. Although the difference between patience and waiting for JWST is kind of redundant. Or I will say I did time working on my JWST proposals brilliantly. I started looking at it on Monday morning, and I spent a few hours on it on Monday, because you shouldn't start proposals too early, because then you spend too much time on them. And by Tuesday, they had canceled it. So I managed to do remarkably little work for this particular exercise. All right, so can you do any better? 1 every 3 to 10 years is a painful rate. At the moment, we're solving this with tenure. And now we're going to just keep going. As I said, this is a project best done with tenure and a supportive department, because you do need to keep it up for a decade. Okay? That's how long we've been doing it now. You get lots of other things. As I said, I've mentioned some things about the SN progenitors. You can find the Cepheids in all of these galaxies. There are other variables. You can look for dwarf galaxies. So they just all being used for that. Reynolds tried to do this with archival HST data. They also ended up with a candidate, but the problem is the archival HST data is so sparse that it's very hard to decide whether you have a false positive or not. Is because in general, what you really have is like 1, 2, or 3 epochs. And it's just not enough to control for everything that could go wrong in the world. LSST turns out to be more or less useless. LSST gives you only 50% more supernova, because it turns out that while the south gets all of the galaxy, the north got all of the local star formation. So you can see 2/3 of the local star formation from the north, and you can only add 1/3 by going to the south. And it's standard exposure. I mean, it's a rinky-dink telescope. It's a crummy, 4 or 5 meter by the time you're done, and they integrate for 30 microseconds. And so basically 1 year of standard LSST exposures is the equivalent of one of our LBT epochs. So you could do this as a special survey, but it's going to, you're not going to add that much, and so you'd still be stuck having to do it for 10 years. It's not a bad thing to do, but it's not good. It adds something, but not a lot. The only thing that could really do this 10 times better is W first. W first could do this in a sample of galaxies going to 30 megaparsecs instead of 1 megaparsec. It would again require a special survey, because they're planning on doing this. But at the moment, this is the only way you could do it 10 times better. And so your choice, at the moment we're going with patience, but maybe you can do that faster. OK, and I'll end there with the logo of a somewhat random survey.
Thank you, Chris. Any questions?
So one other way to search for such remnants, black hole remnants, would be they accrete mass from their environment such that become X-ray sources, so you don't see anything. And then, so the question is, well, first, how many would you expect to be in configuration of an X-ray binary where there would be a donor or some fallback or something?
So, we actually have looked at this for actually the thing I'll talk about in whatever the next session of whatever we're doing. If you try to do population synthesis models, the fraction which should end up in a Roche accreting configuration is very small. And in fact, If you go through the numbers, it's actually SS433 is a miracle. That in the sample of supernova remnants we know about, to have SS433 is very unlikely. And so SS433 is it's sort of one interacting Roche-Loeb binary in a sample of, say, 50 supernova remnants. It's sort of a way you can define a sample. And the actual fraction should be like 10 times below that. So there should be some fallback onto whatever compact remnant you have, right? They're not, not like the fallback supernova, but it takes nothing, right, to run these things at Eddington, right? It's 10 to the minus 5 solar masses per year, whatever. And so there are various models for that. They actually tend to be surprisingly faint and decay fast. And the problem with the X-rays is what I just mentioned, is you're looking for soft X-rays by and large, because, well, first of all, it's the only place where most things have sensitivity. But you're looking for soft X-rays from something which is surrounded by 10 solar masses of ejecta. And it basically takes no mass to absorb away all of the soft X-rays. So early time follow-up is probably not going to get you very far. And so the question would then be is if you go back and look for supernova remnants, which is mainly a galaxy or maybe Magellanic Cloud thing. And there are no obvious examples of something which is just slowly accreting something, because the other things known to be associated with supernova remnants are all wind accretors, neutron star wind accretors. And the problem is then once you sort of say is I just look for accreting binaries in general, the problem is then you don't know how to do statistics. I know of lots of HMXVs. I don't know how to turn the HMXVs into something trivially statistical.